In this video, I'll give you some tips for solving the ALEKS problem called Interpreting a Born-Haber Cycle. This problem is going to give us a Born-Haber cycle. It's going to be different for every problem, and we're going to be asked 3 questions. Number 1, we're all going to be asked to calculate the lattice energy of the product. Number 2, we're going to be all asked to calculate the heat of formation. Then number 3, we're all going to be asked a slightly different question. It's going to vary from one problem to the next, but don't worry. I'm going to give you enough information that you'll be able to answer that question number 3, no problem. So the first thing that I want to do is go through and label the 5 different parts of the Born-Haber cycle. It starts right here. This is step number 1. This is step 2. This is step 3, step 4, step 5. Step number 1, which is this right there, that distance right there, that is our enthalpy of sublimation, delta H sub. The second step, this is our bond energy, breaking that halogen-halogen bond. Step number 3, which goes all the way to the top there. Don't get distracted by the dashed line. That's just to help you read that point on the axis. Step number 3, which goes all the way up to the top, that is our ionization energy. Step number 4 right here is our electron affinity. And then the last step, number 5, that is our lattice energy. Now, the first question, like I said, we're all going to have the same first question, and it's asking us to calculate the lattice energy for this substance. And that is going to be just simply the absolute value of the difference between the beginning point and the end point of that lattice energy step. So it needs to be an absolute value, meaning that you need this to be a positive number, total difference between these two steps. So don't do a final minus initial thing. For mine, I'm starting at 750. I'm going all the way down to 200. And that is a total difference in terms of how much energy is being lost. Total difference of 950 kilojoules. Again, you want this to be expressed as a positive number. That's just the way that ALEKS wants it. Okay, so next question, we're going to be asked to determine the heat of formation, the enthalpy of formation. The enthalpy of formation is the difference between the starting point and the final point on the Born-Haber cycle. So it's going to be this distance right there, starting and final. And this one, you are going to pay attention to sign. So here you're going to go final minus initial, the delta H of formation. That is going to be your final energy minus your initial energy. For me, my final energy is negative 200. My initial energy is 0. And you do want to include the sign here. Got to have the sign in that one. So question number 3 is going to vary from one person to the next, but all of the variations of question number 3 pertain to making changes in the energy of these 5 different steps. So it's going to say something like this step gets smaller, but this step gets bigger, and how it is asking ultimately, how does that affect the stability of the product of this particular reaction. So I'm looking at one variation of the problem right now, and it says that suppose both the heat of sublimation and the XX bond enthalpy were bigger, would this product be more stable or less? So here's how you're going to answer that question. And it's going to give you 2 different scenarios. So mine is saying that the sublimation has increased and the bond enthalpy has also increased. Those are the 2 scenarios that I have. And it's asking me what happens to the stability. So we're going to tackle these scenarios one at a time. We're just going to only think about one, and then we'll think about the other as well. And what we're going to do is find the area of the Born-Haber cycle that corresponds to that scenario. So it's asking me about the sublimation right there. And then it's telling me that the enthalpy of the sublimation has increased. So that means that instead of it being this amount, it is actually just going to be some larger amount. But it's not going to tell you how much the enthalpy of sublimation has increased. So you just know that it's bigger. So the enthalpy of sublimation, instead of going to here, it's just going to go a little bit higher. So I'm going to say, okay, so we're going to start here. And then instead of going to this spot, my enthalpy of sublimation is going to go a little bit higher. Now, remember, all we're doing is focusing on sublimation right now. We're not going to think about the bond enthalpy yet. So if the enthalpy of sublimation increases, but the bond energy doesn't, because remember, we're not thinking about that yet. If this moves up, all the other lines on the graph are going to move up as well. Everything is going to go up with it because the only thing that we've changed is this spot, which means that this gap stays the same. It's just been shifted up. This gap stays the same. It's just been shifted up, etc. And we're going to walk that all the way through the whole entire graph. And then we're going to move on to situation number 2. This is saying that the bond energy also increases. So my bond energy gap is right here now because I've shifted it up, and we're going to increase that gap as well. So instead of going this high, we're going to say maybe now it goes this high, and this is going to get shifted up as well, and this gets shifted up, and this gets shifted up as well. That's our final product. So everything got moved up, and now the actual question that it's asking is, how does that affect the stability of this guy? Okay, so if the line moved up, the final ending point of your product, if that line shifted up, the energy, if we have an increase in the energy of our products, high energy, that means that it is less stable. If the energy goes up, the product is going to be less stable. And if the energy goes down, then the products are going to be more stable. So if we have a decrease in the energy, then it would be more stable. Now, there are going to be some situations on this. You got to be super careful. There are going to be some situations where ALEKS throws some situations at you where one causes the line to move up and the other causes the final line to move back down. And in that case, you're going to have to say, you don't know what you can't make a prediction about what the stability is. So let's consider another situation here, because this can be a little bit tricky until you get the hang of it. So I'm reading another problem, and it says, suppose the electron affinity and the bond enthalpy were smaller. So now my scenario is that the electron affinity has gone down and the bond energy has also gone down as well. And remember, we're going to just take these one scenario at a time. So if the electron affinity decreases, right there, the electron affinity decreases, that means that this value numerically, and we're just talking about the absolute value here, the absolute total value, the gap between these levels is going to shrink. So instead of going from here to here, we're now going like to there, and that's going to cause my product line to be shifted up as well. So just that step alone, that increases the energy of the products. Now it's saying bond energy, that's scenario number 2, bond energy decreases. So this gap between these lines decreases. So instead of going from here to here, we're now taking this down maybe to here, and that means that we're going to move this line down. So that's going to go down. This line is going to go down with it. This line is going to go down as well. So one of these transformations, the electron affinity, this right here we saw caused the product to be less stable. The bond energy going down causes the product to be more stable, and we're not going to be able to make a prediction about stability unless we can actually calculate how much these lines are moving. So for this particular scenario, we would be able to say we couldn't tell. We don't know how this is going to affect the stability. Let's just do one more, because these, I think, well, first of all, I think they're kind of fun, but second of all, they are kind of tricky. So we'll do one more, and I feel like if we do one more, then you're definitely going to have the hang of it. So the third one I'm looking at says that the bond enthalpy got smaller, and wait, that's what we just did. Let's look at a different one. This one says the bond enthalpy gets bigger, and the electron affinity gets bigger as well. How's that going to affect the stability? So if the bond energy gets bigger, that means that the gap here is going to go up. This line is going to move up. This line's going to move up. This line's going to move up. We've increased the energy in our products. That means that this is going to be less stable. If the electron affinity increases, that means that this gap is going to get bigger. So this line is going to move down. This line is going to move down. This would cause our products to be more stable. And there's another situation where we're not able to tell. We can't make a prediction because one of these scenarios causes the energy to go up and the other one causes the energy to go down. I believe in you. I know you can do this problem. Good luck.